Hello class, today we're going to discuss two types of speed associated with an object like this point P moving in a circular path. Notice that one kind of speed we can talk about is how fast it's covering distance along the circle, and another speed we can talk about is how fast that angle is changing with respect to time. As far as the distance that's being covered, notice that's just the length of that arc associated with the movement. So that's no different from, for example, if you recall from your algebra class, if you have a object like a car moving along a straight line, remember that we can find speed by just dividing distance by time. And really, that's the only kind of speed we can talk about here. So the notation we used rate or R for speed, we use D for distance, and we use T for time. And if we cross multiply and solve, we also get a formula for distance as RT. Now, when it comes to movement along a circle, that's not the only kind of distance we can talk about. But one thing that changes is when speed gets any kind of direction, it usually gets the name V for velocity. And since along a circle, the distance being covered is the length of an arc, we change D to S for arc length, and T remains the same. Now, if we solve this formula for S, we get S equals VT. Now, as far as this object that we discussed up here, that's the only kind of motion it can have. But when it comes to the object moving along a circle, we can also talk about how that angle is changing. And that brings us to the notion of angular speed. And just as linear speed is the distance covered divided by time, angular speed, denoted by omega, this is lowercase Greek omega, looks like a W, but it's read omega. We get just basically how much the angle theta is changing with respect to time. Now, the two distances, interestingly enough, are related. As we just mentioned, omega is theta over t, and V is S over T, or the arc length over T. But if you remember from our last lectures, S is nothing but R theta. That's how we find arc length. We discussed that formula before. So if we just replace S with R theta, we get R theta over T. And if we split the R and write it as R times theta over T, notice the theta over T here is of course the same as this, theta over T. So we can write it as R times omega is equal to R omega. So there is the formula that is giving you the relationship between linear speed and angular speed. And of course, you can solve it for omega as well. And you would get omega equals V over R. So you need to be comfortable with both of these formulas because we'll be using one or the other depending on the situation that we encounter. So this is all very simple, but really fundamental and important. So make sure you absorb it before we proceed. Okay, there's a real simple example here to your left. Example 1, using linear and angular speed formulas. Suppose that point P is on a circle with radius 10 centimeters and ray OP is rotating with angular speed pi over 18 radians per second. Find the angle generated by P in 6 seconds. I want you to pause the video and see if you can figure it out on your own before you come back to see the solution. Okay, as you can see, basically we start with the formula omega equals theta over t. For omega, we substitute pi over 18. Theta is what we're looking for, so that remains unknown. And we divide by the time, which is 6. Then we go ahead and solve for theta. Now, a more algebraically sound approach may actually be to take the formula omega equals theta over t and to solve it for theta first. So you can do that easily by cross multiplying, and you get theta equals omega t. What I mean is you can just imagine there's a 1 there, and then you can cross multiply. Remember that if whenever we have a over b equals c over d, you get these cross products are equal. So you get AD equals BC. That's one of those algebraic facts that can make you solve these simple equations very quickly. So you always want to remember that principle of cross multiplication. So now you go ahead and plug in for omega, which is pi over 18, and the time, which is 6 seconds, times 6 seconds. And if you reduce here, you get 3 down here, so you get pi over 3 radians. Remember, the units of the pi over 18 were radians per second. So the seconds cancel out and they leave you radians. You always have to make sure that your units make sense. Otherwise, there's a problem with the formula. So that's how you do that simple problem. All right. Now take a look at the second part of this problem, which wants you to find the distance traveled by P along the circle in 6 seconds. Go ahead and see if you can do it on your own before you come back to see the solution. All right, so as you know, this time we're going to be using the arc length formula because that's how much distance gets covered by the point when it moves around along a circular path, the arc length. So that's the formula that we use. And in this case, we know that if you go back to the original problem, the radius of the circle was 10 centimeters. So that's where we get the 10 here. Replace the r with 10, and theta, of course, is pi over 3 because we know that's how much of an central angle was swept by that movement. So then you just multiply those out. That's where the pi over 3 comes from. In part C, we're going to find the linear speed. And again, remember, linear speed is just the arc length divided by time. We just found the arc length covered. It was 10 pi over 3, and we divide that by 6 to get 10 pi over 18. Now, just to give you a little algebraic refresher, remember when you have one fraction divided by another, we had a nice shortcut for that, which was the outer product over the inner product. So AD over BC. So if you take 10 pi over 3 and divide it by 6/1. Then you do the outer product, which is 10 pi over the inner product, which is 18. Then you know that 2 goes into 10 5 times and into 18 9 times. So that's where we get our 5 pi over 9. And of course, the units are going to end up being centimeters for distance and seconds for time. Okay, so that's a very simple example, and make sure you understand it before we move on. Okay, next let's take a look at this problem on your left. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. They want you to find the angular speed of the pulley in radians per second. Well, when they give you 80 revolutions per minute, they're actually giving you the angular speed, but it's just not in the standard units for angular speed, which is radians per unit of time. And in this case, they want it in radians per second. So they're showing you some approach here, but I'm going to show you an easier way to approach it on the right here. So we can just say omega equals 80 revolutions per minute, and we're going to use unit factors to get to our desired answer very easily. So remember, first thing I'll do is I'll go ahead and translate that revolution into radians. So you know that 1 revolution around the circle corresponds to 2 pi radians, correct? And 1 full circle, remember, that's 2 pi radians. And the other thing we can take care of right away as well is we can take care of the minutes, because they want the answer in radians per second, and this one is given to you in minutes. So again, we know that 1 minute corresponds to 60 seconds. In this way, you take care of the whole thing in one shot with the proper unit factors. Notice that these two fractions that we multiplied here, they're called unit factors because basically the numerator and denominator represent the same quantity, same as here. 1 minute is the same as 60 seconds as far as quantity is concerned. So now we just need to, and also notice that we have revolutions here, so we needed revolutions down here so that they cancel out. And we have minutes here so that they cancel the minutes we had down here. So notice the only thing after cancellation, if we cancel all the things we can cancel, minute is going to cancel minutes, and revolution here is going to cancel revolution. And notice the only units left now are radians and seconds, which is exactly what we wanted. But let's continue with cancellation. We can also cancel out, we know that 20 goes into 84 times, and we know that it goes into 63 times. So that's that, and that should be all the cancellation that's possible. So we get omega equals 4 times 2 pi, which is 8 pi. Downstairs we have a 3, and that's going to be radians per second. Okay, so that's all there is to the first part of this problem. So theta equals 8 pi over 3 radians per second. I'm sorry, omega equals 8 pi over 3 radians per second. All right, so now they want you to find the linear speed of the belt in centimeters per second. Now, that's going to be quite simple actually, because as you know, linear velocity and angular velocity are related. If you look back in the video, you'll see that linear velocity v is nothing other than the radius times the angular velocity. Now we just found the angular velocity, and that was, if you recall, 8 pi over 3 radians per second. So we go ahead and replace r with 6, and we go ahead and plug in 8 pi over 3 for the angular speed, and here we can cross cancel those out. That gives you a 2. So we end up with 16 pi, which is approximately 50 centimeters per second. That's how fast that revolution is taking place. All right. Let's take a look at one more example. In this case, you have a satellite that's orbiting the Earth. And we know that the satellite itself is actually 1,600 kilometers above the surface of the Earth. And we know that it takes 2 hours to make one full revolution or one orbit. And they give you the radius of the Earth as well. So that's 6,400 kilometers. And they want you to approximate the linear speed of the satellite in kilometers per hour. So I would actually like you to give this some really good thinking before you come back. It will be very good for you. You should be able to figure this out, but it may take some thinking. So make sure you give it some really good thinking before you come back to take a look at how we do it together. Okay, welcome back. So the first thing that we need to do is we need to make sure we know what this orbital radius is. So the radius of the orbit is going to be basically this 6,400 plus that 1,600. So we're going to go ahead and add the 6,400 kilometers to the 1,600 kilometers to get a radial orbit of 8,000 kilometer, or rather an orbital radius. So the next thing we need to know, if we want to know the linear speed, we need to know how much distance was covered in a given period of time, right? So, and we know that that distance is basically going to be the circumference of that circle, right? So that's the next thing we're going to compute. In other words, S is just going to be r theta. In this case, the orbital radius is r, which is 8,000 kilometers. And we know that a full revolution corresponds to an angle of 2 pi radians. So when we multiply that out, we get 16,000 pi kilometers. Of course, that's just the distance that was covered during the revolution, and to get the actual linear velocity, we need to take that distance and divide it by the time that it took for that distance to get covered. So we get 16,000 pi kilometers divided by, and remember this took place in 2 hours, so 2 hours. And this is when we get the final linear velocity to be, if we simplify it, we get 8,000 pi kilometers per hour. All right. So of course, if you plug that into a calculator, so we get 8,000 pi, and depending on the level of accuracy that they need, I believe here they were looking for to the nearest 1,000, so that'll be approximately 25,000 kilometers per hour. So that's basically how you go about taking care of a problem like that. That's the first part. Now let's take a look at what they want in the second part. Now they want you to approximate the distance the satellite would travel in 4.5 hours. Go ahead and pause the video, see if you can come up with that distance, and come back and we'll finish it off together. Okay, so of course for that's going to be another arc length, so we need to go back to our arc length formula. And if you remember in the beginning of the lecture, we said v equals s over t, and we did solve this for s to get s equals vt. And now we know the v, so that's going to be 8,000 pi. And we're going to multiply that by, let's put the units in to make sure it makes sense. That's in kilometers per hour, and we're going to multiply it by 4.5 hours. And we basically get, so if we multiply 8,000 by 4.5, we end up with 36,000. Oops. 36,000 pi kilometers. And if you plug that in, you'll realize that this is going to be approximately 110,000 kilometers. Okay, so again, these two formulas are quite simple, and the relationship between them is a nice simple relationship, but very important and fundamental. So make sure you understand all this before you try to do your homework. And as always, if you have any questions, let me know and I will try to put up a video with the answer as well. And that should do it. Take care and be safe until the next time that I see you.